guys, today we're going to have continuity of functions. Can you trace the broken lines without lifting your pen or without passing through the same broken lines more than once? If you need more time to decipher this question, you can press pause. Continuity of function is like tracing the broken lines without lifting your pen and without passing through each portion of the line more than once. Now, let's take a look at the three graphs presented on the screen. Which do you think demonstrate or exhibits continuity of functions? Again, you can press pause if you need more time. In these three graphs, only letter A exhibits continuity of function. If we trace the graph, let's have letter A. Take note that we can trace the graph in A without lifting our pen and passing each portion once. While here in option B, if we trace this graph, we need to lift our pen in order to trace the other parts of the graph. The same is option C, wherein we need to lift also our pen in order to trace the other portion of the graph. So hence, only the graph illustrated A shows continuity of functions. Now let's describe continuity of functions formally. A function is said to be continuous at the number A if all the following conditions are satisfied. First, f of A exists. Second, the limit of f of x as x approaches A exists. And the limit of f of x as x approaches A is equal to f of A. If any one or more of the given conditions fail, the function is said to be discontinuous at a number. Let's work on example number 1. Determine whether f of x equals x squared minus 2x minus 3 is continuous at x equals 1. We now show that the function satisfies all the three conditions. So we show that f of 1 exists by evaluating the given function at x equal to 1. So we will have 1 squared minus 2 times 1 minus 3. Simplifying that, we will have negative 4. Therefore, f of 1 exists. Now let's show whether the given function satisfies the second condition. We show that the limit of x squared minus 2x minus 3 as x approaches to 1 from the left is equal to the limit of x squared minus 2x minus 3 as x approaches to 1 from the right. Now we evaluate the given function at x equals 1, so we will have 1 squared minus 2 times 1 minus 3. We also evaluate the given function at x equals 1, so we can see that they are both equal to negative 4. So hence, we can say that the limit of x squared minus 2x minus 3 as x approaches 1 is equal to negative 4. Hence, the limit x squared minus 2x minus 3 as x approaches to 1 exists. We can see that the given function satisfies the second condition. Now, what about the third condition? We are asked to show that the limit of x squared minus 2x minus 3 as x approaches to 1 is equal to f of 1. Now, we can see that this is equal to negative 4 and f of 1 is also equal to negative 4. Then we can conclude that the function satisfies the third condition. So with this, we can confidently say that f of x is continuous at x equals 1. We use graphical method to confirm our conclusion or our answer that the function is continuous at x equals 1. Using GeoGebra or Desmos, we can have this graph and we can plot the point at which we have x equals 1. So here we have x equals 1. Now if we will trace the function, we can see that we can pass through this point without lifting our pen. Hence, we can say that f of x is continuous at this given number. Now let's move on to the second example. Determine whether f of x equals 2x squared plus 11x plus 5 all over x plus 5 is continuous at x equals 0, and the second one is x equals negative 5. We determine first that the function is continuous at x equals 0 by using the three-step method. Okay, we evaluate f of 0. So we will have 2 times 0 squared plus 11 times 0 plus 5 all over 0 plus 5. Simplifying this, we will arrive at 5 over 5, which is equal to 1. Hence, we can say that f of 0 exists. It satisfies the first condition. Now let's have the second condition. Okay, the limit, we have to determine whether the limit of f of x as x approaches to a exists. So we have to get 2x squared plus 11x plus 5 all over x plus 5 as x approaches to 0 from the left is equal to the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches to 0 from the right. So we need to show that these two are equal. So evaluating this, we will have 2 times 0 plus 11 times 0 plus 5. We will have 0 plus 5, and we need to show it's equal to this. We will have 0 plus 5 in the denominator. So simplifying this, we will have 5 over 5, which is on the other side is we have also 5 over 5. They are both equal to 1. So hence we can say that the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches to 0 is equal to 1. So therefore, this limit exists. Okay, so we can say that it satisfies the given condition, the second condition in particular. So we can conclude that this limit exists. Now let's take a look at condition number 3. We show that the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches to 0 is equal to f of 0. Okay, let's take a look. This is equal to 1 and f of 0 is equal to 1 also. They are equal. Hence, we can conclude that f of x is continuous at x equals 0. We support our answer that it's continuous. Okay, This is the point on the graph where x is equal to 0. Okay. Now, if we trace this graph, we can pass through this point continuously without lifting our pen. Now, let's try whether the function is continuous at x equals -5. We again use the three-step method. We evaluate the given function at x equal to -5. So 2 times -5 plus 11 times -5 plus 5 all over -5 plus 5. Okay, to simplify this, this will be 2 times 25 minus 55 plus 5 all over 0. Now in the numerator, we also have 0. So this is an indeterminate form. Therefore, f of -5 does not exist. Now, since it does not satisfy the first condition, we can already conclude that, say that f of x is discontinuous at x equal to -5. In other words, we can also say that f of x is not continuous at x equals -5. Now let's support our answer using a graph. Okay, so graphically, we can show 2x squared plus 11x plus 5 all over x plus 5 using this line. Now, since we cannot use -5 for x, this point will be represented using an unshaded dot or a hole. So if we will trace this graph, we will be interrupted by this hole in order to continue tracing the graph. Therefore, we can say that f of x is not continuous at x equal to -5. Now let's take a look at example number 3. Investigate the continuity of the function f of x, which is defined by the two function x squared minus 1 where x is less than 2 and x plus 2 where x is greater than or equal to 2. Again, we use the three-step test, so we determine whether f of a exists. Now, since we will evaluate the given function at x equals 2, we will use this function since at this function we can get a condition that x equals 2. So if we will have f of 2, we will evaluate x plus 2 at x equals 2. So simplifying that, we will have 4. So f of 2 exists since we have a real number. Now what about if we will check whether this function satisfies the second condition? We have to prove that the limit of f of x as x approaches to 2 from the left, okay, is equal to the limit of f of x as x approaches 2 from the right. So we evaluate in the limit of f of x as x approaches to 2 from the left, we will evaluate, okay, the limit of x squared minus 1 as x approaches 2 from the left. Whereas the limit of f of x as x approaches to 2 from the right would be the limit of x plus 2 as x approaches to 2 from the right. Now evaluating the two limits, we will have 2 squared minus 1. On the other side, we have 2 plus 2. So we will have 4 minus 1 on the other side. Okay, on the other side, we will have 4. Now, we simplify, then we conclude since 3 is not equal to 4, then the limit of f of x as x approaches 2 does not exist. Okay, since we have arrived at two different values. So with this, we can say that f of x is not continuous at x equals 2. Now we support our answer using a graphical method. Okay, so if we trace the graph, okay, we will be interrupted here when we reach this point. There is an open hole. Then in order to proceed to the other part of the function, we have to jump in order to trace this line. So from here, we can say that f of x is really not continuous at x equals 2. Okay, so that's it. Now let's have example number 4. Investigate the continuity of the function f of x equals to the absolute value of x minus 3, where x is not equal to 3, and the constant function 2, where x is equal to 3. Okay. From here, we again prove or show that this function satisfies the three conditions, so that we can say that this function is continuous at x equals 3. So we shall use, for f of 3, we shall use this function because at this function we can see that x is equal to 3. So f of 3 is 2, therefore f of 3 exists. Now, we evaluate the limit of f of x as x approaches to 3 from the left equal to the limit of f of x as x approaches to 3 from the right. Then we will have 3, absolute value of 3 minus 3 equal to the absolute value of 3 minus 3. Is this really equal to each other? Okay, we will have 0 equals 0. Okay, we were able to get that the limit of f of x as x approaches to 3 equal to 0. So the limit of f of x as x approaches to 3 exists. Okay, this shows that the function satisfies the second condition. So what about the third condition? Okay, we show that the limit of f of x as x approaches to 3 is equal to f of 3. Now we get the value of the limit of f of x as x approaches to 3. We have 0. However, f of 3 is equal to 2. Therefore, they are not equal. So we can conclude that f of x is not continuous. Okay, not continuous at x equals 3. Okay, we support our answer with the graphical method. Okay, so take a look. Since in the absolute value of x minus 3, x is not equal to 3, this should be an open hole or an unshaded dot. So if we will trace this, then we will be interrupted by this hole before proceeding to the other part. Then to trace this, we have to jump. Okay, from this, we can say that f of x is discontinuous at x equals 3.